Okay, now we talked about finding that area under the curve last time, estimating those with a rectangle. All right, so we're going to build on that. First of all, we're talking about a definite integral. A definite integral. A definite integral means I have bounds. I have specific bounds that I'm looking for, and I'm looking for an integral is the area under the curve. We already talked about that. Now we're looking at the words that go with all of that. All right. So if I'm talking about an area under the curve, we are going to be looking at a net area, which is the sum of the area above the x-axis minus the sum of the area below the x-axis. Okay, here's the moral of the story. The x-axis is what breaks this apart. So if I have this x-axis right here and I have this whatever curve, all right, and I'm going right here from A over here to B. If I have above the x-axis all of this area here that I am making pink, ooh, fun to color. Man, I should do more coloring. It's fun. Nice. So this area and this area over here on this right side, also pink, because this is above the x-axis, making it positive. Well, what's happening with that little dip in the middle? Let's change my color here. Let's go blue. Why not? It's below the x-axis. So what did we just say was happening with the area below the x-axis? Yes, it's negative because we subtract that off. So here's the moral of this story. All of the area above the x-axis is positive. The area below the x-axis is negative. So the net area means all of this up here I'm going to add, and everything down here I'm going to subtract. It doesn't mean that it's not going to show a negative value here, but you know you subtract it because it is below that x-axis. Okay? And so think about those rectangles that we did previously. How am I going to get as accurate as possible here? Am I going to have 4 rectangles? No. If I have infinitely many rectangles, that's what's going to do the trick, right? The more rectangles I have, the better this is going to look. So if we have infinite rectangles, that's going to be as tight and as tiny as possible. This will be the most accurate. That doesn't make sense. Will be the most accurate area. So here's my question to you. If I want to have something that approaches, that goes to infinity, what concept are we talking there as I'm approaching something? That's the key word. Yeah, limits, right? You mean they don't go away? No. Forever. They're here forever. Okay, let's talk about the concept here, this definition of a definite integral. Basic concepts is what's happening. Basic concepts is what's happening. So I want to point that out to you. This symbol, it looks like a real elongated S. This is an integral symbol. Learn it, love it. It means it's a big elongated S for summation. Like we did our Riemann sums, we added up those different areas of rectangles. That is what's happening. And if I go from A to B here of f of x dx, have we seen this before? You mean the differential was important? Yay! Here it is. This is telling me that I have this differential here with respect to x. When we are setting this out, this is called the lower bound because this is the interval that I'm doing the integral of. And this is the upper bound. All right? Those are the words that we're looking for here. All right. We are going to, of course, have formulas that go with this, but for now, we're learning the concept. I just keep beating that drum over and over. So our concept here is this. The limit as my change goes to 0, right? As my change of x goes to 0, my change goes to 0, of k is equal to 1 to n of our generic formula. That's what's happening. As I am looking, let me just draw a little quick right here of whatever this is happening, right? I have this rectangle. As my change here in x, as my change, as my delta, as my change goes to 0, that means my rectangles are getting skinnier, 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 skinnier. The skinnier they get, as I approach a width of 0. That doesn't mean I land on 0. I got to have some kind of a rectangle there. But it is infinitely small, and that's how I get infinitely many rectangles in here, because my change is getting closer and closer and closer to 0. Do you see what's happening there? All right, so that's the concept. This is still my height. This is still my width of that rectangle. I'm just saying my width of the rectangle is getting infinitely smaller. So we are going to use this concept here, this formula, in order to rewrite our integrals. All right? That's all we're going to do. Okay, check this out. I need a new page. Let's do this one. We have, here is example 2. We are going to represent the given limit as a definite integral on the interval. All right, so I am given the limit as delta approaches 0 of this summation from k is going from 1 to n, because remember we have n that we're looking at. We don't know how many rectangles we have. We're just making it smaller and smaller, of 3x sub k asterisk squared plus 2x sub k asterisk plus 1 change in x. And I'm going to be on the interval from 1 to 3. Literally, all you're doing is converting between the limit notation and the integral notation. So I'm going to flip back here for a second. My limit notation is on the interval, the upper bound and the lower bound. That's my interval here. My function that we have is going to be my function. My dx is the change in x. I'm replacing that with the change in x. That's literally what's happening. So if I have this, I have an upper bound and a lower bound. So as I integrate, I'm going to go from 1 to 3. I am subbing this into my function. So this is just the x value that we're subbing in for. So I've got 3x squared plus 2x plus 1 dx, because that's my change in x is going to be my dx. You can put parentheses, you don't have to. We kind of talked about that. All right. Boom, that's it. Yeah, we're not getting any crazier here. That's legit it. Can I take a limit notation and put it in definite integral notation? We're not solving this out at this point. We will. Sit tight. But at this point, we're just making sure you understand this is what an integral means. An actual definite integral means I am taking infinitely many rectangles over this function. That's it. Okay, let's try one more here. What about 5.2.34? We are going to take this Riemann sum and write as a definite integral. So I'm given the limit as in lies, not in, delta approaches 0 of k is going from 1 to n of 4 minus x sub k asterisk squared delta x on the interval from -2 to 2. Put that in a definite integral. Yep, -2 to 2 on my integration. 4 minus x squared dx. Boom, that's it. That's all she wrote. Not bad, right? You're just seeing the relationship between infinitely many rectangles and a definite integral. That's the connection that I want you to make here. Overall, pretty easy. Cool. What a way to start this off, right? I know, it's